Hello. In this video, we are going to look at vector fields and line integrals. So let's start off with vector fields. A vector field f of x, y assigns a vector to every point in two dimensions. In our two-dimensional space. Okay, so that's just our definition. The idea is that you go through and you take a point and you plug it into this vector field formula, and out comes a vector, and that's the vector that's at that point. So let's go through and look at an example. So suppose we had f of x, y equals xi plus yj. All right, so to go through and figure out what a vector, so this vector field, you could plug a point into this and it would produce a vector. That's going to be the vector that's at that point. So that's the minimal definition here. But if you wanted to visualize what a vector field looks like, what you can do is you can go through and you can actually plot points, kind of plot vectors, by taking points and plugging them into the vector field formula. So that's what we're going to do to really wrap our heads around this example. So we're going to need a two-dimensional axis to plot our vectors on. All right, and then from there, what you want to do is you want to just take points and plug them into this to figure out what vectors go at that point. So we could start off by plugging in 0, 0. And if you do, you're going to get 0i plus 0j. So we're going to get the 0 vector. We get the 0 vector here at the origin. And then we can go through and plug in 1, 0. Right, so let's just pick a spot here. We'll say that's 1, 0. So take that and plug it in. We're going to get 1 times I plus 0 times j. So that's going to just be I. And we could go through and plug in 0, 1, and we'll get j. You could plug in -1, 0, and get -I. And just to finish up, we could do 0, -1, and we will get -j. All right, and so to go through and plot these, we just want to, so that's going to be here, here, and here. So we just want to draw little vectors at those spots. We can use a different color to make sure to differentiate. So we've got a vector here, and the vector I points to the right, points in the positive x direction. So we could just put a little vector there. Let's see, can we see that on top of the line? Let's just put it a little above the line, make it so we can see it. And then we could go through and do the negative of that. And then we could do vector j, and then the negative of that. All right, and we've got the start of our vector field graph. And so we can go through and can plug in more values. We could plug in, oops, forgot to change back to black. We could plug in 1, 1, and we'll get I plus j. We could plug in 1, -1, right, and get I minus j. And we could plug in -1, 1, get -I plus j. We could plug in -1, -1, get negative I minus j. And then we could go through and graph those. Right, so I plus j, that's going to be the vector that goes 1 unit in the x and 1 unit in the y. So it's kind of like a combination of these two vectors here. If you just kind of combine them, that's going to be our vector. And then we've got that one there, that one there, and that one there. All right, and these vectors should be longer than these other vectors, the ones that are on the coordinate axis. The length of I plus j is going to be square root 2, while the length of I is just 1. So they should appear a little longer than the ones that are on the axis. Okay, and of course you could keep going beyond that. So you could go out to f of, you could go through and find f of 2 comma 0, and that would be 2i. And you could do f of 0 comma 2, that would be 2j. Now you could do f of 2 comma 2, and that would be 2i plus 2j. And you could quickly kind of figure out what this looks like. Right, so let's go through. So if you have 2i, right, so that's going to be at the, that's going to be at 2, right, 2 comma 0. And then that one should be, that vector should be twice as long, right? If you've got I, 2i is twice as long as that. So we need a longer vector. So if this little guy was the one that was at 1, 0, then we need something that's bigger than that. And sometimes when you go through and you graph these, they won't necessarily be to scale, right? So it doesn't have to be exactly twice as long as this. It just needs to be longer, just to kind of represent the fact that it's you're getting longer as you're moving away from the origin. And then you could do the same thing, at some of these other points, and you could kind of quickly figure out, what this looks like. Right, so we need a longer vector, and then a longer vector. Let's just move that over a little bit, and then a longer vector, and then we need, longer vectors on the diagonal here. And you could go through and plug in to figure out what vectors would go in these spots here. But what the vectors are going to be, they're going to be a combination of these two. So it's basically going to be like you mixed these two together. And so you're going to get a vector that's kind of like that, right? So it's going to go right 1 up 2. And then the vector, here will go left 1 up 2. And so on. You can just kind of fill this in. Oops. Anyway, so you can get the idea of what this looks like. Hold on. There we go. All right, so if we just observe, so how would we describe what this looks like? As we move away from the origin, we move away, the vectors become longer and longer as we move away, and they move out in a direction, right, that is represented, kind of by where they're located, right? So if you're on the axis, you continue to move in the direction of you move in a straight line. I guess what I'm trying to say is you move in a straight line away from the origin. All right, so if you start off on the x-axis here, you'll move further away on the x-axis. If you start off on the y-axis, you'll move away in the direction of the y-axis. If you start off on the diagonal, you'll move away. What I'm saying here is that if you go through and kind of drew a line through this, it should kind of be in line with where you started. So if you start here, you're going to stay on that trajectory, on that line as you move away as well. So it's not just that you're moving away faster and faster, it's also that you're staying on the trajectory that you are, from the origin. Okay, so you stay along that same line. Okay, so what are vector fields? Like, what's the purpose of them? So other than just going through and having a vector at every point, what do you use vector fields for? All right, so vector fields are used to represent either movement or forces, or kind of a combination of the two, depending upon the context. So examples are, typical examples are fluid flow, such as movement or the force from the flow, force from the fluid. Or a river, could be a river, for example. Or you could have, common things are tidal. Sometimes you see tidal movement / forces. You can also see sometimes, flow of heat, because heat flows like a fluid. Or you might see the modeling of magnetic forces. Okay. And so just to be clear here, so why do I put, it's a fluid flow such as movement or the force from the movement? It depends upon the context, kind of which you're thinking of. So you could imagine that you've got a river, right? So just imagine you've got a river, and you could have arrows in that river that point in the direction that the river is moving. Okay, so you could go through and you could model the direction the river is moving, with arrows. And those arrows would be a vector field. So the vector field could represent that. However, you could also think of it in terms of the context that those arrows also are the force from the movement of the river. And so it really depends upon the context, whether you think of it in terms of whether it's, the arrow represents a movement, in terms of the flow of some fluid is moving in that direction, or it represents the force from the fluid. Okay, so they're kind of used interchangeably, and so anyway, that's one of the things that vector fields are used to go through and model. And so in this example, in this case, if we go back to our original vector field here, you could think of it, if this were represented flow of a fluid, it could be that there's there's a like a hose or something, and the end of the hose is right here at the at the origin, and water is kind of flowing out from that center. And so if you're a particle that's sitting near that origin, then you'd end up kind of flowing in this direction, right? So you'd end up flowing away from the origin, or you'd end up flowing in this direction, away from the origin. So if you start off, you're a particle that's near the origin here, and you move faster and faster as you move away. Maybe there's a downhill or something like that. The hose is at the top of a of a little hill or something, and so you're flowing away. The flow of the water away from the origin becomes faster and faster as you move away from it. All right, so it starts off, you move very slowly, and then you move quicker and quicker. Or you could think of it if you were, standing right in this spot. If you picked a spot here and you said, you know what, I'm going to stand right here. Okay, now, this would be a pretty big hose if you could stand in front of the flow. But if you're standing there, you could think about it like the water is pushing against you, and you have to hold against there's a force from that fluid flow, and you're trying to withstand it to stay in that spot. Okay, so vector fields can either model the flow of a fluid, or they could model a force, from withstanding that flow. And so that's why I go through and kind of break it up into the two cases. It really comes down to the context, whether it's representing movement or whether it's representing the force that would come from that movement. Okay, and so that could be, example, like I said, example for a river. If you go through and you can, go through and Google tidal, tidal vector field. I don't know if tidal vector fields will bring it right up, but if you go through and you do enough searching on the internet, you can find maps that represent tidal movement, and the way in which those maps frequently represent that movement is with arrows. Those arrows is an example of a vector field. The arrows represent the flow of the tide, or you could think of it, if you were to try and hold steady in a specific spot, they would represent the force from that tide that's pushing against you. Okay, and so anyway, that can be extended to other things. It's not just fluids, but fluids are kind of the most common. But you could have heat or magnetic forces that could also be represented with vector fields. All right, let's go through and look at another example. All right, so these are common examples that are just kind of, normal ways to introduce yourself to vector fields. So the first one is that fluid flow away from the center. So it's good to see an alternative example like this. And the same idea goes. So at 0, 0, this time, the graph's going to be undefined. So we'll skip over that, right? We'll have a 0 in the denominator. But we could go to 1, 0. If we had 1, 0, so now the x value is 1, the y value is 0. So if y is 0, that means we're going to have a 0i. Then we'll have a minus 1j divided by 1 squared plus 0 squared. That's going to be the square root of 1. And so we're just going to end up getting minus j. All right, we could try 0, 1. If we do 0, 1, now the y is 1 and the x is 0. So we're going to have just I divided by the square root of 1. And so we're just going to get the vector I. And if we went through and typed in negatives of these, so if we did negative 1, 0, we would get positive j. And if we did 0, negative 1, we would get negative I. So what are those going to look like? Let's just pick some spots here. All right, so at 1, 0, we get the vector negative j. At 0, 1, we get the vector I. I points in the right, points in the positive x direction. At negative 1, 0, we get the vector j. So negative 1, 0, that's here. And then at 0, negative 1, we get the vector negative I. looks like that. And you could go through and do the diagonals. So we could do f of 1, 1. And if you do that, then you're going to get, so we've got, if we plug in 1, we're going to have I minus j over the square root of 2. So that's going to be 1 over root 2 I minus 1 over root 2 j. All right, so it may have been a bit since you've gone through and looked at lengths of vectors, right? But if you go through and calculate the length of this vector, it's going to be 1 over root 2 squared plus 1 over root 2 squared, right? And so if we take 1 over root 2 and square it, we get 1/2 plus 1/2, and then the square root of 1/2 plus 1/2 is going to be the square root of 1, which is 1. So this vector has a length of 1. So it means it's the same length as these blue vectors. So when you draw the resulting vector here, so that vector should go, it should go to the right and it should go down, right? A vector that goes to the I is going to go to the right and negative j is going to go down. But you don't want to draw it as the same. You don't want to draw it as a kind of a combination of these two, because it should be shorter than that. It should be the same length as these two. So that's the one thing that you kind of have to try. Maybe that's about the right length, right? And we want to put that right where the 0.11 would be. All right, and then we can go through and try a few more. So this guy is going to be like that. And again, you want to try to draw it so it's the same length as these. And like that. And like that. All right, and then just like before, we could move a little further out. What happens as we move further out? We could do f of 2, 0. All right, so now we've got, again, x is 2 and y is 0, so that's going to be 0. So we're going to have minus 2j over the square root of 2 squared, so that's going to be 4, plus 0 squared, so that's going to be 0, so over the square root of 4. So we're going to have negative 2j over 2, which is just going to be negative j. And so if we go and plot our vector, that's the same result that we got at 1, 0. So we get the same length here. All right. And now if you go through and plug in the others, if you do, negative 2, 0, 2, 0, 0, 2, what you're going to find is you're going to find the same thing is true. So all of these vectors are all the same length. As we move away, the vectors do not get longer like they did with the last example. Okay. And the same thing is going to be true along, if you go along the diagonal, you go to, negative 2, 2, we're going to have, the same vector that we do here. And so on. And so you get a consistency of, for the lengths of the vectors. And so the vectors don't get longer as you move away from the origin. All right, so in terms of interpreting this result, so if we go back to our first example, we were moving away from the origin and we were moving away faster and faster. And so again, you could think about it like you've got, some type of a hose or a source for your fluid, and then you're flowing away from that source. How would you describe this? This looks like rotation, right? So the idea is that there is like a whirlpool around your center here, and you're moving around that, around that whirlpool. And then again, just like in the first one, you're moving faster and faster as you move away. You're not moving faster and faster as you move away. In this case, there is a consistency in terms of the speed of the whirlpool around the center. So you've got the same speed near the center as you do further away. So you're not moving faster and faster as you move away from the origin. All right, so this is a common example that you see where this division by a square root of the, if you take the length of the numerator here and put that in the denominator, then that's going to cause this effect where you have the same speed. All right, so if you don't see anything in the denominator like this, that typically means that the vectors are going to get longer and longer as you move away from the origin. And then if you do see something in the denominator like this, that's the length of the numerator, then that's going to cause this effect where you don't see the vectors get longer and longer. Okay, so our vector fields, are they restricted to 2 dimensions? No, they are not. You could go through and have a vector field in 3 dimensions. All right, so I'm not going to even try to sketch a 3-dimensional vector field, but you could go through and that's just a Google, 3-dimensional vector field, and you could see what they look like. I mean, it's basically the idea is that you're going to have 3 dimensions. You're going to have your 3-dimensional coordinate axis, and then you're going to go through and you're just going to have a whole bunch of arrows in that 3-dimensional space that are going to point in the direction of, again, of either movement or force, depending upon the context. Okay, but they're very difficult to graph without some type of a computer tool. All right, so the next thing we're going to look at are something called gradient fields. So if a vector field is the origin of taking the gradient of a function, then we say that the vector field is a gradient field. And the lowercase f, that the function that you took the gradient of to get your vector field, that is called the potential function. Okay, so again, we're using capital F here as for our vector field. If you've got a vector field and it comes about by taking the gradient of a function, then that vector field is called a gradient field, or if you want to get the word vector in there, a gradient vector field. And F is called the potential function of the gradient field. Let's see an example for that. Suppose f of xy equals x squared y. All right, so find the gradient field. All right, and so to do that, you just go ahead and you just take the gradient of x squared y, right? So if we go through and calculate the gradient of f, right? So if f is x squared y, the gradient of f, the way they calculate the gradient is you take the derivative of your function with respect to x, multiply that by I, take the derivative with respect to y, multiply that by j. So the derivative of x squared y with respect to x is going to be 2xy I, and the derivative with respect to y is going to be x squared j. And there you go. That's your vector field. All right. So if we just take capital F and set it equal to that, we can see that we do get something where we can plug in xy coordinates and this will produce vectors, right? So if we plugged in 0, 0, we would get the vector 0. If we plugged in 1, 0, we would get the vector, it looks like j, right? 1 squared times j. If you plugged in 0, 1, you're going to get the vector 0, 1, so it looks like it's going to be the 0 vector as well. All right, and so you can go through and you can plug in points and out will come vectors. And that's what our definition of a vector, that's what our definition of a vector field is. And so by going through and taking the gradient of functions, you produce a result which can be interpreted as a vector field. Okay. And that's it for our, coverage for vector fields. All right, so a fairly brief, short section on vector fields. We're now going to use vector fields moving forward in all of the future sections. So you do want to make sure that we understand them, but there's not really a lot more to it than that. So let's move on to our second topic for this video, line integrals. All right, so what is a line integral? Well, like many of the other integral topics, it starts off as a problem that you want to solve. So what is the problem that we want to go through and resolve that's going to end up turning into a line integral? All right, so that problem is going to be, suppose every point in R2 in 2 dimensions is given a value f of xy. All right, so we've got a function, you plug in a point and out comes a number. A number is produced and we're going to just say that that's the value at that point. All right, suppose also curve C is defined parametrically by x equals x of t and y equals y of t. All right, so we've got a curve C as well. All right, let's kind of produce a little picture for ourselves here. Now we're working in 2 dimensions. We've got, there's curve C. Okay, and again, it's defined parametrically. So we could go through and produce the points on curve C by plugging in t values between A and B. So that when t is A, we're at this point. When t is B, we're at this point. Now, there's no way to represent this, the fact that we've got a point, a value at every point, but we're going to assume that we do. All right, so the question that we want to solve, which again, all these integral topics always start off with a question. What is the sum of the function on the curve? All right, so the idea is what we want to do is we want to go through and add up all of the function values that are on the curve, not everywhere else, just on the curve. So if you think about it this way, so we want to start off here at our initial point where t is A, we start off there, we go through and we figure out, all right, so what's the function value here? So you're going to take that point, plug it into your function and get a value. All right, and then you're going to move along, you're going to increment a little bit, and you get to another spot on the curve, and you're going to say, all right, what's the function value here? All right, and then you're going to increment again. You're going to say, what's the function value here and here and here and here? You're just going to move along the curve, calculating the function value at each point, and then when you get to the end, you're just going to add all those function values up. So we want to know, what is the sum of the function values that are on the curve? That is our question that we want to go through and answer. All right. How do we do that? Okay, actually, let's move to the next space because I don't know that we have enough space on this one. I'm going to redraw that picture again because we need it. All right, so we've got our curve C. We've broken this. We've already discussed this idea of moving along the curve and calculating the value every small distance until we get from one end to the other. All right, so the way that we could go through and calculate that value, the sum of all those functional values on the curve C, the way that we could do that is we could pick a little interval, pick a piece here. We're going to call that the ith interval. So it's going to be a representative piece. Okay, and then what we want to do on that ith interval, let's just go through and kind of sketch it off to the side. It's not entirely necessary, but let's just say that we've got that ith piece. It looks something like that. Okay, what we want to do is we want to find a spot somewhere in there where we can go through and calculate our function value. So let's just pick a point in there. It doesn't matter exactly where. I'm just going to pick a spot. And what we want to know what is the value of the function at that spot. We want to be able to find the function value. Again, remember, every point in 3 dimensions is assigned a value f of x, y. So to find the value, to find f of x, y at that point, we need to use our curve. The way that you do that is you're going to go through and you're going to say, all right, we're going to assume t sub I, we're going to assume that this is the t value is the location on the curve there. We're going to t sub I star is going to be the location on the curve, the t value for the location on the curve. All right, so t sub I star, let t sub I star be the t value. At that location. You say t value, what t value? What are you talking about? Where t come from? Okay, it came from our curve is defined parametrically in terms of x of t and y of t, where t varies from a to b. Okay, so since our curve is defined in terms of t, we can go through and say let the t value, let t sub I star be the t value at that spot. Okay, so once you've done that, you can go through and you can find x and y by taking that t value and plugging it into the parametric equations. All right, so we take our t sub I star and we plug it into our parametric equations, and that gets us the x and y value at that spot. So we went from t to over to x and y. And then once we have the x and y value for that spot, we can then take the x and y value and plug it into f. All right, so the value of f there f of x sub I star y sub I star. All right, so that's going to be the value of f at that spot. All right, so we've got our ith interval here. We picked some spot on there, and that red spot, it could be at this end, it could be at this end, it could be somewhere in the middle, it could be anywhere. You're just going to pick a spot somewhere on your ith interval. You're going to pick the t, let the t value, t sub I star be the t value for that location, and then from that you can plug that t value in to x and y to get to your x and y function to get the actual xy value there. And then from there, you can take those values and you could plug it into f to get the actual function value. All right, and so that if this seems complicated, this is the way that it works. All right, so you're going to start off with t value, use the t value to find xy, use the xy to find f. All right, so once we've got f, so we've got a value for this interval. However, look at when I described this, I said, you just pick a value, you're going to find a value here, and then you're going to move along, find a value, move along, find a value. Well, the only issue there that remains unresolved is how far do you move along? How, because your function value is going to end up being different depending upon how far, right? So if I go through and I'm standing here and I calculate, so let's actually try and wrap our mind around a specific example. Suppose you have a hot plate, right? If you're not familiar with the idea of a hot plate, the idea is that you've got a flat surface, and at every point on that flat surface, you have a temperature. Okay, so let's say we're on our hot plate, we're standing here where where our finger is there or whatever, we're measuring the temperature on our plate at this point. And let's say it's 75 degrees, then you move over 74 degrees, then you move over 73, 72, 71, 72, 73, 74, 75. Let's go say it goes down and back up again. Well, so if you're just adding those up, those temperatures, right? If you take big steps along your curve and you just add up those values, or you take tiny steps, you're going to end up getting your resulting amount is going to end up being dependent upon how big a step you take. And so the length of these intervals needs to be taken into account to offset that. And so the way that we can do that is we can go through and we can say the length of this piece is going to be change in s. All right, and change in s, so if you recall, so s is length. So from earlier topics you've seen, like arc length, we use s for arc length. So we're going to say that the change in s is going to be the length of this little curve segment. Okay, and what we can do is we can throw an I on there to represent the fact that you could have different lengths along your curve. So they're not all the same, but the length of the ith piece, the one that we're working with, is going to be change in s sub I. Okay, and so once we have kind of added that, to go through and find the f value for the ith piece, we need to go through and combine the length with the value, right? So with the value. So how do we combine length and value into an amount of f? On the ith piece. That's not that complicated. You just multiply the two. So the amount of f on the ith piece is going to be f of x sub I star y sub I star times change in s sub I. All right, so that's the amount of f for that specific piece. Okay, and now again, if you recall from earlier topics, when we're working with something that we're summing up, and once we find a way to represent one piece, then the next thing is that we just go through and we add up a bunch of pieces. All right, so the total amount of f on curve C is the summation I equals 1 to n of f of x sub I star y sub I star change in s sub I limit as n goes to infinity. All right, so now what we're doing is we're adding up all of the values that all these amounts that we got. We're adding them up for each piece, and then we're taking the limit as the number of pieces goes to infinity, and then that's going to get us the exact amount of f that's on the curve. All right, and so the way that you transition from this, you're going to go through, you're going to have f, and then these x sub I stars become just x and y. And then change in s, so you recall from previous integrals, change in x, change in y, they become ds. And then we're going to go through and represent the fact that we're summing along the curve. We're going to represent that with a c. Okay, this here, this is the conceptual definition for a line integral. Right, you can go through and you can kind of shorthand it, and it frequently is shorthanded into FDS. So the way that you can look at this, or the way to think about it, is this is telling you, what is a line integral? It's the product of a function times a length. Function times length. ds is length, f is function value. All right, and you're doing you're doing the function value times length, and you're doing that along the curve. All right, and that's the way to kind of translate this into words. This is all kind of conceptual. It's telling you what a line integral is. It's the sum of f times function value times length on curve C. This is not this formula here. This is not how you go through and actually evaluate a line integral. So this is not used to evaluate line integrals. It's one of the more confusing parts of vector calculus that really throws off students, is that this formula that you end up getting here, this is not actually used to go through and evaluate line integrals. It's a conceptual definition. All right, that's really important. But so what is the formula that you go through and use to actually evaluate line integrals? Because you do want to be able to go through and evaluate these. All right, well, there is a formula. Okay, and what that formula is that it's going to involve us using t. T is going to be the key, and the parametric equations here are going to be the key, because that's our kind of our access to t. So t comes about through these parametric equations. And so what we're going to do is we're going to go through and kind of translate this using the parametric equations into t. So, all right, so to go through and evaluate a line integral, should say maybe to evaluate a line integral. To evaluate a line integral, use the parametric equations to translate into t. All right, so how do we do that? What we're going to do is we are going to start off with f of x comma y ds, and we're going to go through, we're just going to translate everything here. All right, so recall, right, we have x equals x of t, y equals y of t. And where'd that come from? That came from our definition. That came from our parametric equation right here. That's our definition. All right, so that comes from curve C. So it comes from, use your parametric equation. So we have curve C tells us that x equals x of t and y equals y of t. So we're going to go through and rewrite this, and we're going to replace the x with x of t, and we're going to replace the y with y of t. Again, those come right out of your parametric equations. Now, what about ds? Okay, well, this is going to come from our earlier formula for arc length. Okay, so if you recall, from our parametric equation form for arc length is the integral from a to b of the square root of x prime of t squared plus y prime of t squared dt. So it's probably been a minute, but this is the formula for, this is the arc length for parametric equation. Okay, now if you start off here and you go through and you differentiate both sides, you take the derivative of both sides. If you take the derivative of s, we're just going to write ds for that. And if you differentiate an integral by the fundamental theorem of calculus, the derivative of an integral, those cancel, and you're going to get the square root of x prime of t squared plus y prime of t squared dt. And so you can use this handy formula. You can just take it and you can just pop it right in where the ds is. All right, so we're going to get the square root x prime of t squared plus y prime of t squared dt. And then once we've gone through and translated everything over into t's, now we can go through and just put our bounds, and our bounds are going to be in terms of t. So the a and b, where'd those come from? Did I just make those up? Nope. They came from the initial problem. You go all the way, not to vector fields, but you go back to the beginning, a and b, again, came out of our parametric equation. So the parametric equation is the key to going through and translating the line integral into something that you can actually evaluate. So you're using the fact that C is defined in terms of x of t and y of t with some bounds for a and b. That's the key throughout this. The x becomes x of t, the y becomes y of t, the ds is translated into x of t's and y's of t's, and then everything is now in terms of t, and so we can grab the bounds in terms of t from our parametric equation and pop those in. And so this formula here, this is the key to going through and evaluating line integrals. This is how you evaluate line integrals, is using this formula. All right, so you cannot evaluate line integrals directly in terms of the conceptual formula. You always need to translate over into this alternate form with t in it. All right. Let's do some examples. These examples are both in 3 dimensions. So just a quick comment on that. Everything we did here is in 2 dimensions in this derivation. If you were to translate this into 3 dimensions, you would just add a z equals z of t, and then you would just draw the curve in 3 dimensions. And then you'd have f of x, y, z. So all of this whole thing, you could just add a z, draw in 3 dimensions, add a z, and so on. Add a z there, add a z sub I. Everything here you can just add one more coordinate to, and then it doesn't really change anything. All right. So suppose you're asked to go through and evaluate. Now you'll notice, the first thing you'll notice about this problem, all right, evaluate. Oh, hold on, I actually need to finish actually writing it down. You have x equals cosine t, y equals sine t, and z equals t, and t is defined from 0 to pi over 2. Okay, so now that it's actually written down, so the first thing you'll notice is that they start you off in the conceptual form. That is going to be pretty normal when you go through and evaluate line integrals. So normally they're going to start you off in the conceptual form, and you're going to have to translate over into the evaluation form. All right. And so, just in terms of the conceptual form, looking at this, we can kind of see what this is asking us to do. It's asking us to move along this curve. And at each point along this curve, we're going to go through and we're going to find the function value, which is x squared y, and we're going to multiply by a length. Okay, and so that's the idea, that you can be able to go through and look at this and see this is function times length along the curve. All right, so with that said, let's go through and translate this. How do you translate it? So you want to just go through and kind of follow the steps that I did here. So what did I do? I went through and I took the x and I rewrote it in terms of t. So we want to take the x here and rewrite it in terms of t. How do you do that? You use your parametric equation definition. So what is x? It's cosine t. So we're going to have cosine squared t. All right, and now you want to take the y and translate that in terms of t. How do you translate y to terms of t? You just use your parametric definition. Okay, and then ds, how do you translate that? You use that arc length formula, right? It's written right there. So you want to go through and take the square root of the derivative squared. And so we're going to go through and do square root. We want to take the derivative of x, so that's going to be negative sine t, and square it. Then we want to take the derivative for y, that's going to be cosine t, and square it. And then take the derivative for z, which is going to be 1, and square it dt. And then what should our bounds be? Again, look over to your parametric equation. Your parametric equation is the key to everything here. All the translation all comes out of this again and again and again. It comes from the bounds for t from our parametric equation. All right. And then from there, you just want to go through and simplify this. So we got cosine squared t sine t. This is sine squared plus cosine squared, which is going to be 1. 1 plus 1 is going to be 2. And so we're going to get the square root of 2 dt. All right. And then so to go through and evaluate this integral, this is a u substitution. We have u equals cosine t, and du equals negative sine t. So you can put in a negative there and offset it with a negative there. And then this integral is going to become, move the root 2 out front. And then the bounds, take 0, plug it in, you're going to get 1. Take pi over 2, plug it in, you're going to get 0. And don't forget that negative there. And then we're going to have u squared du, and that's going to be negative root 2. The antiderivative, that's u to the third over 3 from 1 to 0. So plug in 0, you get 0. Plug in 1, you get 1/3. So we're going to have minus 1/3. And this is going to equal root 2 over 3. Okay. So there's a example of evaluating a line integral. And to interpret your result here, so what does this result mean? It means that if we started at the point 0 on this curve, and we walked along that curve, measuring at each point how much what our function value is, when we got to pi over 2 and added all those function values up, the sum of the function on the curve is going to be root 2 over 3. All right. Let's do a second one so you can see another example. These are fairly straightforward once you know what you're supposed to do. All right. So here we've got a second example, and we want to do the same thing. So you start off, they give you the conceptual form for the line integral. You need to translate this over into the value, the form in terms of t, the kind of the parametric form or the evaluation form. And to do that, you're going to need to use your parametric equation. Now, the thing that makes this problem a little bit harder is that they didn't give you the parametric equations. So fear not, you should be able to find them using techniques from earlier in the semester. So we did go through and find the equation for line segments. The way that you can go through and find the equation of this line segment is to first find the vector that goes between these 2 points, and then you can use the equation for a point and a vector to turn that into a equation of a line. All right, so the vector between these, let's just use v. You could subtract the coordinates. All right, so see, how do we want to do this? Let's take this and subtract this way, right? So we're using this as the second point and this as the first point. If you do that, you get 1 minus 3, that's going to be negative 2. 2 minus 1, that's going to be 1. 2 minus 0, that's going to be 2. All right. And then once we've got the vector, you could think of this as a direction vector for your line, and this is a point for your line. And if you've got point and direction vector, you can use point and direction vector to find the equation of a line using the parametric form. All right, and so what does that parametric form look like? It looks like x equals, you start off with the point value, and then you take, add or subtract, in this case, subtract, but t times the direction vector value. So we're going to have minus 2t, and then we're going to have y equals 1 plus 1t, or just plus t, and then z equals 0 plus 2t. All right, and so that guy can be translated just into 2t. And so we've got our, oh, and then finally, when you go through and you define the parametric equation this way, where you have a starting point and a vector that goes from one point to another, your t values are always going to go from 0 to 1. And you could check that out, right? Just plug in 0. What happens if you plug in 0? All these t values go to 0, and you're going to get 3, 1, 0. That's this point. Plug in 1, you're going to end up doing 3 minus 2, that's 1. 1 plus 1, that's 2. 2 times 1, that's 2. All right, and so it will always end up working out this way, that you'll end up getting the line segment from 0 to 1 if you do it the way that I went through and showed it here, where you just subtract the points to get a vector, and then take your first point, and then add t times the direction times your vector values. All right, so that's maybe the heavy lifting for the problem. If you haven't gone through and found the equation of a line in a while, but from there, it's just same thing as the last problem. So we just want to go through and plug everything in here. So what are we going to have? We're going to have y. What's y? Y is 1 plus t. So we're going to have 1 plus t squared. What's z? Z is 2t. All right, and then ds, what's ds? It's the square root. And then you want to take the derivative and square, right? So the derivative of x is going to be -2. So we're going to have -2 squared. The derivative for y, that's going to be 1. So we're going to have 1 squared. And the derivative of z is going to be 2. So we're going to have 2 squared dt, right? And I guess we'll go down here. Oh, and then the bounds go from 0 to 1. And so we're going to have 0 to 1, and then it's just a matter of multiplying all this out. So if you multiply this out, you're going to have, this is 1 plus 2t plus t squared times 2t. Actually, let's do this. Let's take this 2 and move it out. And then what are we going to get here? This is 4 plus 4 plus 1. That's 9. The square root of 9, oh, that's a 3, right? So we're going to have 2 times 3. And then what was I saying here? So yes, you're going to have 1 plus t squared times t. So you're going to have 1 times t, that's going to be t. And then when you multiply this out, you're going to have 2t for the middle term times a t. So we're going to have 2t squared. And then finally, you're going to have t squared times another t. So we're going to have t cubed dt. And so this is going to be 6. And then the antiderivative here, that's going to be t squared over 2 plus 2/3 t cubed plus t to the 4th over 4, evaluated from 0 to 1. And so we're going to get 6 times 1/2 plus 2/3 plus 1/4. Okay. All right. So what is that? That's 6 times. So if we use, I guess the common denominator is going to be 12. So we're going to have 6/12 plus 8/12 plus 3/12. Okay, and so what's that? That's going to be 14, 17, 17/12 times 6. And then let these reduce 17/2. All right, and so there's our second line integral value. And again, same thing. The idea is you're moving along. You're starting at 3, 1, 0. You're moving over to 1, 2, 2. And at each point, you're just calculating what is the function value there. And you're just adding all of them up. And that is what the line integral is. Okay, so the second topic in this line integral section is called a work integral. This is also thought of as a line integral over a vector field. That's why it's in the line integral section. It's a line integral over a vector field. All right. So what this is going to end up being is it's going to be the same thing that we just did, except instead of having a function value at every point, we're going to end up calculating the work at every point, the work. Now, been a little while since you've looked at work, but we'll review that. All right, so let's kind of start it off the same way that we started off that earlier problem. So what do we have? So suppose we have a vector we have a vector field. That defines a vector at every point and you could have two-dimensional or three-dimensional space here. I'm going to use kind of two-dimensional space, but this all can be extended to 3 dimensions. All right. And then again, same thing. Suppose we have a curve defined parametrically. Oops, not 0. It doesn't have to start at 0. From A to B. Okay, and so what our problem is going to be is to go through and find the work done by a particle moving along the curve C. All right, so let's go ahead and do a visual, but this time let's just do the visual directly on the next page so I don't have to draw it twice. And we'll do in 2 dimensions, but this could all be extended to 3 dimensions. All right, so this time we are going to do a visual for the vector field. I'm going to go through and I'm going to just put some vectors on here. Now the vectors, I'm going to just, to make it simple, I'm going to draw very simple vectors, but it could be any type of vector field. All right, so the simple vector field we're going to use is we're just going to do vectors that just point to the right here. These are just representative vectors. All right, so you've got a vector field. You got some vectors from your vector field. And then we have a curve that's moving through the vector field. We'll just pick some starting spot here and go through and say we've got some curve that's moving through our vector field. And that curve is curve C. All right, and so what we want to do is we want to go through and find the work done by a particle that's moving along the curve. Okay, all right, so hold on. To do that, actually, I forgot about something here, which is a good thing I came back to this. So what we're going to do here, the curve C, the parametric definition, we're also, instead we're going to look at the vector function definition. All right, so curve C could also be defined in terms of a vector function, R of t. And so again, this is something that if you go back to when we defined vector functions and parametric equations are interchangeable. So we could think of this instead of parametrically as x equals x. We are going to end up using this x of t, y of t in the definition, but we also are going to end up using r of t instead at various points. So these we need to be able to interchange these. So suppose suppose we go through and think of this as r of t. You could translate to r of t. And then once we translate to r of t, we can also then go through and find capital T of t. This is the unit tangent and we're going to need this as well. So we're going to need x equals x of t and y equals y of t, and be able to take those and turn them into r of t. And once you've got r of t, be able to find the unit tangent t of t. Okay, so these things are all, from earlier videos. If you go back and watch the vector function video, we talk about translating parametric equations and vector functions. And then if you watch, there's a later video where we cover the unit tangent as well in that same earlier chapter. Okay, sorry about that. Yes, I should have done that before we got to the picture, but I forgot. All right, so let's say we've got our picture here, and the idea is what we want to do is we want to go through and figure out the work that's done. So to do that, this is going to, might be like, work, what does this have to do with it? Okay, well, if you think about moving along this curve, one of the ways that you could think about it is you could think about it again in terms of movement, and that movement could be modeled in terms of the unit tangents. All right, so if you start off at this initial point, if you calculate the unit tangent at this initial point, the unit tangent could say, hey, you're moving in this direction. And then you could go a little further along and you could stop here and you could say, all right, I'm going to calculate the unit tangent there. And the unit tangent would say, all right, you're moving on top of the line, but to make it look clear, I'm going to draw it next to it. You're moving in this direction. And then you get here, and you can use the unit tangent, and the unit tangent will say, hey, you're moving in this direction. And then you get here, the unit tangent says you're moving in this direction. And then you get here, and the unit tangent says you're moving in this direction. So you can use the unit tangents to model your movement along the curve. All right, and that's a critical piece to being able to go through and think and try and wrap your head around how this could translate into work, is that you've got these vectors. They are modeling the movement of something that particle is in, like water, right? So this is like, think of this like the river. There's a river that's flowing along here, and that's modeling, the blue vectors model the flow of the river. And then the black vectors that are on here, those came from the unit tangent. Those model a flow, the movement of a particle. So you've got, or particle is a common term, but you could think about it like if this were a river and you were walking along, you could think about this like you're a person, you're a particle. You think of a person walking along through the river. And the idea is the river is pushing on you. It's applying a force to you. So the river is applying this force onto you, and you're moving along through that force. If you've got a force and movement, then the combination of those two is something that we model with work. All right, so earlier in the semester, we defined work in terms of vectors. Right, if we have F is a force, right, and D is a distance that an object is moving, then the work that is done by the force on the object moving the distance is given by work equals force dot product with distance dot product. All right, so this is the work done by the force on the object moving the distance. All right, so that's kind of a little refresher there that we're going to need here, is that we've got force vectors, we've got movement vectors, and so we need to be able to go through and take force vectors and movement vectors and combine them into work. And the way that we do that is by using that earlier definition. And this definition comes from the dot product section. So you can see this is actually common throughout this last chapter in this course, that gets into vector calculus, is we start grabbing topics from all over the semester and combining them, and that's what we're doing here. So we've got a work definition from the dot product section, and we have our vector function definition, and our unit tangent definition. Those are all going to be used here. All right. So now that we've reviewed work and we've talked about how we've got vector field vectors from the vector field, and we've got movement vectors. The question is, how do we combine those to go through and calculate the amount of work that's done? What we want to do is we want to do something very similar to what we did earlier in this video. So we want to pick an interval. Let's just pick this interval here. We're going to call that the ith interval. Okay, and what we want to do is we want to first find the work that's a work value for that interval. All right, so let's go through and maybe try and sketch what that interval could look like. This is the same thing we did earlier. So you get kind of a sketch. This is maybe this curve here. We want to pick a spot on that. Just this, a lot of this is the same as from earlier. We're going to pick a spot on there, and we want to find the work that's done at that spot. Okay, to go through and do that, we first need to know the location for that spot. So we're going to say, hey, let t sub I star, see, this is the same start. Let t sub I star be the t location for this point. Okay, once you've got the t location at that point, you can go through and similar to before, we can find x and y. So you can find x and y. X sub I star is going to equal x of t sub I star. So this, like I said, we're using all the tools here. We're using the parametric equations. And we got y sub I star equals y of t sub I star. All right, and so that's going to give us the x and y. And then at that point, we can go through and we can find the vector field vector that's there. So we can find the vector field, the blue arrow. The blue arrow, we could find that by taking x sub I star and plugging it into our vector field definition, right? So that's our capital F. So that's our, oop, I didn't even write it here. Right? That's capital F. Suppose a vector field capital F. All right, so do need that. So we're going to take the location of our point in terms of t, translate into the x and y. Once you've got the x and y, plug that into F. So that's given us the blue arrows. All right, that's not giving us the black arrow. That's the unit tangent. So this value gives us the blue arrows. All right, so we need to find F. So that gives us, so you can think about that in this particular case, it would be this, right? That's our vector field arrow. That's F. That's what we just found. We also want to find the unit tangent. Oops. Change that back to black. So we also have the unit tangent at that location. All right. And so the unit tangent, that's going to be the tangent vector. So we can draw that in as well. All right. So, and they don't have to be the same length. I don't know why I'm drawing them the same length, but the idea is that you've got vector field, unit tangent, and the idea is that this is modeling the force, this is modeling the movement, and so we can go through and find the work at x sub I star, y sub I star by taking the dot product of f of x sub I star, y sub I star dotted with the unit tangent at x sub I star, y sub I star. All right, so that's going to be the work that's done for this little piece is going to be the dot product of the force vector, that's our f, and then our distance, how far we're moving, and that's our d. All right, so you got those two pieces. Okay, and so now the last thing is that very similar to this, just like when we were going through in the line integral and we were finding the vector, so we were finding the function value, and we're like, all right, well, how much function value? The length does need to be a part of this. Okay, so what we're going to say is the length of this is change in s sub I. Okay, and so the last piece is that the work for that piece, we're going to end up multiplying that by change in S sub I, and that's going to give us the work for the ith piece. Okay, so from there, you can go through and just throw a summation onto, throw a summation from I equals 1 to n, the limit as n goes to infinity, and then we've got our force, x sub I, y sub I, right, star, star, dotted with unit tangent, x sub I star, y sub I star, change in s sub I, and then this turns into the integral, over the curve of f dotted with t ds. This is our one of our conceptual, because there's going to be two, a conceptual definition for the work integral. All right, so the last thing we're going to do, we're going to do something tricky here to rewrite this into an alternate form. So the unit tangent, if you actually look up what the unit tangent is, it is r prime divided by the length of r prime. Okay, and ds, if you go through and look up the vector form, right? So s equals the integral from a to b of the length of r prime of t dt. So if you remember the vector form, so let's throw some t's in here just to make it look a little nicer. All right, so if you recall the arc length for vector functions, this was a definition that we went through and derived in the arc length of a vector function section. If you differentiate both sides of this, you get ds equals the length of r prime of t dt. And so we can go through and replace ds with the length of r prime of t dt. And then the r primes here, the length of r primes cancel. And this ends up turning into c. Well, actually, that's why I didn't put the t's in, because we haven't translated this into t yet. Let's just, yeah, I changed my mind. Change this back. Get rid of these t's. Well, oh, I get fine, I guess. I'll leave them in. Yeah, I'll explain this in a second. All right, so these cancel, and then the r primes. This is the part that I was kind of getting a little confused by myself. Take the r prime dt. That we're going to go through and we're going to represent that with dr. And so this is the alternate form. Is instead, so you've got kind of two conceptual definitions that you'll see. Sometimes you'll see f dot t ds, and sometimes you'll see f dot dr. And the way that you get from this one to this one is by going through and replacing the unit tangent and the ds definition and canceling those. And so the dt, the t variable, is buried inside of the dr here. There's two conceptual definitions for work integrals. Now that we have defined the conceptual form for a work integral, we need to find a way to translate it into a form that is useful for evaluating the integral. So the same thing that happened with line integrals, we need to go through and find a way to do the same thing, right? So the method that you use to translate a work integral from the conceptual form into the evaluation form is very similar to the one that you use for a line integral, right? And the key is to go through and use the definitions that we have for the curve, right? So it all comes out of the curve. So we have x equals x of t, and we have y equals y of t, which you can combine into a vector function r of t. And then we have t varying from a to b. All right, so starting with our conceptual form that we just finished deriving, if we have f dot dr, the way that you can translate this is to first kind of reverse some of the steps that we just finished. So we'll have f, this is f of x comma y. That's just kind of just rewriting this in a longer format. And then dr is the derivative of r. So that's r prime of t dt. So that's just kind of taking the shorthand form and just breaking it out into this longer version. All right. And so from here, if you go through and just plug things in, then you can get to an evaluation version, right? So what is X? It's X of T. What is Y? It's Y of T. So the difference is that X and Y, these are just two different variables here that are in this formula. When you go through and translate them into this form, you've translated them into a single variable, right? So now we have X of T represents a bunch of T stuff here. Y of T represents a bunch of T stuff here. So we're just going to have this whole thing, F is just going to end up just in terms of T. And then of course, R is in terms of T. So we'll have just T stuff here as well. And then with this dt added on at the end, and then so then if you look at this, we've got T stuff here, T stuff here, there's T stuff everywhere. And so we can actually put in some bounds here for T that go from A to B. Okay, and so this formula here is the key to going through and evaluating work integrals. All right, well, I guess these three formulas, but it's really this formula. This is the conceptual form, and then this is the evaluation form, if you will. And so you want to just go right from here, skip down to here. You know, this is conceptual. And then this is for evaluating. All right, so let's go ahead and do a couple examples so that we can see that in action. All right, so suppose we have, they ask us to go through and evaluate f.dr, where f equals xy squared I minus x squared j. And they tell you that C is defined by the vector function R of t equals t cubed I plus t squared j. And t varies from 0 to 1. Okay. So if you're going to go through and take, you know, this conceptual form and plug these things into it and get to an evaluation form, then you need to go through and use this guy here. That's going to be the key. All right, so how do we do that? So there's a couple steps here. So first, the parametric, you can take the vector function and translate it into a parametric equation by taking x and setting it equal to the, you know, the part that's next to the I component. That's the x part of the vector function. And then set y equal to the stuff that's next to the j. That's the y component from the vector function. So we know that x equals t cubed and y equals t squared. All right, and so then from there, you can take this and combine them to get an f that is in terms of t below. All right, so I'm just going to do kind of doing two steps at once here. So I'm going to take these, plug them into this, and then write that in place of the f above. All right, so how are we going to do that, right? So where the x is, you're going to put a t cubed. So we're going to have t cubed. Where the y is, you're going to put t squared. So we're going to have t squared, and then there's another square. And then that is times I, okay? And then minus, now we're going to take x, put it where the x is. And so you're going to get t cubed squared times j. All right, so take a look at that. That thing there, that is f. It has this form, except we've gone through and we've translated over into t by using our vector function / parametric equations. Okay, and so that's what you want to do every time. So you're going to start off with an f. You need to take that f and turn it into an f that has t's in it, and then you're good. Then that's it. All right. So then after that, next we need to go through and replace dr. All right. So to get dr, if you start off with r here, what is dr? Dr is r prime. It's just a shorthand way of writing r prime. And so we need to go through and differentiate this to get dr. So just take r prime. And so that's going to be 3t squared I plus 2tj. All right, and then go through and just substitute that in, all right? So that's what dr is. So just put that in place of dr. So you're going to get 3t squared I plus 2tj. And then last, you do just tag on a dt afterwards. All right, so this is F. This is dr. And then once you're done and you've got everything in t squared, you can simplify and then take the dot product. Oh, and then I forgot the bounds. And the bounds, of course, are just now everything's in terms of t. So we do want t bounds. So we go 0 to 1. All right. And then from there, we can go through and simplify. This is t to the 4th, t to the 7th. This is t to the 6th. That just stays 3t squared. Oops, forgot the t. All right. And then once you've got everything kind of cleaned up, now you just take the dot product. So recall the dot product is to just go through and multiply component wise. So we're going to take t to the 7th times 3t squared. That's going to give us 3t to the 9th. T to the 6th times 2t. That's going to be minus 2t to the 7th dt. And then you can go through and integrate. Get 3t to the 10th over 10 minus what's that going to be? It's going to be t to the 8th over 4. All right, and then evaluated 0 to 1. So we're going to get 3/10 minus 1/4. All right, and then whatever that is. All right, so that's going to be so multiply by 4. So we're going to have 12/40 minus 10/40. So that 2/40 or 1/20. Okay, and so that's the basic idea. All right, so they're all very similar to this. Once you know the steps for going through and evaluating a work integral, it is very much kind of a plug and chug. So let's just recap, right? So to start off, they say go through. This is the instructions. They say evaluate f dot dr, where f is this and r is this and c is this. Okay. And so to do that, you're first going to take your r and you're going to pull out what the x and y are. And you're going to pull out the parametric equations. You're going to translate your vector function into parametric equations. And then you're going to take those parametric equations and you're going to pop them into f to take f and get it so that's all in terms of t. Once you've done that, you're going to take your definition of r, you're going to differentiate it. And then the result, you're going to have two vectors. After you clean up, you're going to go ahead and take the dot product of those two vectors and then integrate. Okay, and so that is how you go through. That's the key to being able to understand and evaluate work integrals, is this notion of translating from this conceptual form over into the evaluation form or the evaluating form. So you've got these two different formulas. This one basically is, it's conceptual in the sense that it's describing what the integral is. All right, what it is it's a product of a vector field vector with a, dr here is representative of the fact that it's you've got a the direction and the distance that you're heading in, right? So this represents the vector field. This represents the distance or the direction that the curve is heading in. And that is what a work integral is it's a dot product between vector field and direction vector. Okay, and so that's what comes out of the conceptual, but in terms of evaluating it, that's useless for actually evaluating the integral. To actually evaluate the work integral, you need to translate it over into t stuff, and to do that, you use the curve. You use the parametric equations and the vector function to go through and translate it into something that actually can be evaluated. So it's critical that you understand that. Otherwise, you'll be hopelessly confused when it comes to evaluating work integrals. All right, let's try one more just to make sure that we reinforce this idea. Again, the instructions are to evaluate f dot dr. The other form that you might see is that the earlier form that from this video. You also sometimes will see f dot t ds. These are interchangeable. Okay, these formulas are exactly the same. You can translate back from this one over to this one by rewriting t, in its unit using the unit tangent formula, as we showed a few minutes ago. All right, so you might see this if they ever ask you to evaluate this. It means the same thing as evaluating this. All right, so they say go through and evaluate this, and they say f equals x plus y squared I plus xz j plus y plus z k. They tell you that c is defined by r of t, and that equals t squared I plus t cubed j minus 2t k. And that goes from 0 to 1. All right, and so we just want to repeat the same steps that we did last time. So first, you need to pull out the parametric equations from this vector function. The way that you do that is set x equal to the x component, set y equal to the y component, and set z equal to the z component. All right, once you've got those, you can then take those and substitute them into f, and that will enable you to translate from just this generic vector field f into a vector field that has this formula with all this t stuff in it. This formula is not good enough. You can't just use this. We can't have a mix of x, y's, and z's. To go through and evaluate work integrals, we need to translate that into t's, and so that's where this comes in. So we're going to have t squared, right? Just take this and pop it where the x is, and then take the t cubed and put it where the y is. Whoops. Cubed. Right, and then squared. Right, so you're taking y, which is t cubed, and then you're squaring it. All right, and then that's times I, and then x is t squared, and then z is negative 2t times j, and then y is t cubed minus 2t k. All of this big monstrosity, this is all f. Okay, except we've plugged in all of this t stuff into it. So now we have f of x of t comma y of t, okay, instead of f of x comma y, which is what this is. So we didn't write it that way, but if you'd actually written it, you could have written it that way, right? This is f of x comma y. This is f defined in terms of x and y. This is now f defined in terms of t by taking these. Oops. Except there should be 3 variables, not 2. The last one had 2. All right, that's all that, and then the rest is, so we've got that's the f, that's the f. So the dr, we need to go through, and to find dr, you need to find r prime. All right, and so we could do that. The derivative, that's going to be 2ti plus 3t squared j minus 2k. All right, and then you could just take that and just pop it in down here below. 2ti 3t squared j minus 2k and dt. And then finally, you'll notice all t's here. We have nothing but t's, and so that means we can change our bounds to be in terms of t. And what are those t values going to be? Bounds are given over here when they described the curve. So we're going to go 0 to 1. All right, and then from there, the next thing we need to do is actually to calculate the dot product of these and simplify. Let's see if we can do that at the same time. So we're going to take 2t and multiply it by this thing. So when you do the dot product, you're going to multiply component wise. You want to multiply the I stuff together, the j stuff together, and the k stuff together. So we're going to get, this is t squared times 2t, so we're going to get 2t cubed. Then here, this is going to be t to the 6th times 2t, so that's going to be 2t to the 7th. All right, and then here looks like we've got minus 2t to the 3rd times positive 3t to the 2nd. All right, so that's going to give us a minus 6. What's that, t to the 5th? All right, and then next we've got t cubed times negative 2. That's going to be negative 2t cubed. And then we're going to have negative 2t times negative 2. That's going to be positive 4t. All right, and let's see, we've got these 2t cubes. Those cancel. We're going to have 0 to 1. Let's see if we can fit this in. I'll write it a little smaller here. Minus 6t to the 5th plus 4t. And then the antiderivative is going to be, so the is t to the 8th over 8, and then the 2 there is going to cancel, the reduce the 8 to 4. So we're going to have t to the 8th over 4. And then what do we got here? This is just t to the 6th, derivative t to the 6th. And here we've got 2t squared. All right, and then 0 to 1, we get 1/4 minus 1 plus 2. All right, and so that's going to equal, what that's 1 plus 1/4 is going to be 5/4. Okay, and so that looks good. And so that's how you can go through. That's 2 examples back to back. And you can kind of see, hopefully, that they are very similar. It's very much kind of a plug and chug. The only thing that you can encounter that can make these problems a little bit more difficult is where you have to go through and find the C. Okay, if they don't give you what the curve is, then you might need to do that. If so, all right, if that were to happen, what you want to do is you want to go through and find the parametric equations first, right? So to go from a curve to parametric equations is, it's kind of the first step. Then once you have the parametric equations, you can then turn those into the vector function by taking the parametric equation for x and multiplying that by I, taking the parametric equation for y, multiplying that by j, and the parametric equation for z and multiplying that by k. Okay, and so that's how you could build up to r, and then from there you'd be able to take r prime. That's the only thing that I could think of that they could go through and do to make these problems much more difficult. Other than that, they're pretty much the same every time. All right, well, that's it for our video on vector fields and line integrals, and I guess work integrals too. Thank you for watching, and I'll see you next time.